This is Mrs. O'Neill for AP Chemistry, Chapter 17, Section 3, Part 4. More about this weak, strong problems dealing with acid-base titrations. So first, yes, again, let's look at that curve. So do we understand that this is now a weak acid with a strong base, and our equivalence point now is going to be greater than 7. We want to remember that when that acid is neutralized, it makes that weak base, that conjugate base, that common ion. So because it's a conjugate base now, it is going to be greater than 7. So you should have already seen this in maybe one of those titration videos and hopefully understand again, where are we on that titration curve and what is actually in our pot at that moment. So again, in the very beginning, we have our weak acid in our buffer area. In our buffer area, we now have what's called this common ion, right? This common ion, this weak acid and some of that common ion, and that's what makes it a buffer because it's resisting change in pH. Again, when we're at the equivalence point, now the acid is completely neutralized, and now we really just have that salt, right? We have that salt solution, and we have that common ion. We don't have any more of that weak acid. And of course, after the equivalence point, now we have no acid whatsoever because now that's the limiting reactant. It's totally gone. It's been all used up. It's been all reacted, and now the equilibrium shifted and making now more OH minus. Now we have an excess of that OH minus. So again, here's our difference between our strong acid-base curve and our weak acid-base curve. So hopefully getting you to understand that the only time we have a buffer region is in our weak acid-base curve. And our strong curve is just we got more of the strong stuff or more of the other strong stuff, right? But in our weak acid-base curve, we need to understand that if we have more weak stuff, we are in the buffer region, and if we have more strong stuff, we're just kind of strong. So I do want to show you one more example of a weak base being titrated with a strong acid. You hardly ever see this, but I still want to make sure that you're understanding, again, the concept of equal at the equivalence point and the concept that we can see it both ways. And we need to understand what we have in our flask and what we're titrating with in our burette. It is really important. So if we are calculating the pH only at the equivalence point, we have our weak base of ammonia, 25 milliliters of 0.1, and we're titrating it with a strong acid, HCl. Again, how do I know? This is on the list. This is not. So why did they give us a KB? Because we're starting out with a weak base. So again, looking at this information, if we're at the equivalence point, that means our moles have to be equal. If we're at the equivalence point, that means there's a shift. If we're at the equivalence point, that means moles of the weak stuff equals moles of the strong stuff, which also equals moles of that common ion. But in this case, now the common ion is going to be the conjugate acid. Well, if we have more of that conjugate acid, that means we want to use the other K. So we're going to calculate that new molarity with the total volume, and again use the opposite K because now we have more of the quote-unquote acid stuff, right? So initial moles of the base, again molarity times liters. At the equivalence point, our moles are going to equal each other, so I don't even have to look at the problem. I can say, well, if I know that I have 2.5 times 10 to the negative 3 moles of our base, if we're at the equivalence point, it's going to equal the moles of our acid. So, which means our conjugate acid is also going to be 2.5 times 10 to the negative 3. So, find our new concentration. So, 2.5 times 10 to the negative 3 moles divided by 0.05. Again, if I have 25 milliliters of our base and our concentrations are the same, I must have had 25 milliliters of the acid as well. So just kind of keep that in mind, right? That was a little tricky. I know that our moles are the same. So how do I know how many milliliters of HCl I added? Well, it's easy. At least in this case, it's easy because our molarity is the same. That means the amount of my volume also had to equal each other. So now we have our molarity of our conjugate acid or of our ammonium polyatomic ion. So now we're going to use that opposite K and solve for H plus. So how do we do that? Again, we're using that KW rearranging. Okay, they gave us the they gave us the KB value of the ammonia, and now we're solving for Ka. So because of that, think of that ice box. What does that ice box look like? Again, products over reactants. And again, this is our reactant this time because it's hydrolysis, right? We're changing the equation, changing the reaction. So our Ka equals our x squared divided by that concentration that we just found of our common ion, but we're going to subtract that point x, right? We're going to get rid of it. We don't need it. We're assuming that 5%. So we're solving for H plus. And what are we going to do to that to find pH? You got it, negative log. So 5.28. That should make sense, right? It should make sense that we're starting with that weak base. We're adding a strong acid. So at the equivalence point, we should actually be less than 7. So that's what we should expect. So if we did use the icebox, again, this is our initial reaction going on. All right, now we have none of this stuff and only our common ion. Well, because of that, now we need a new icebox, right? Because this is going to be a new reaction going on. This is the conjugate acid reaction going on. So we need that new icebox at the equivalence point. So now we've changed things around and now we only have our weak guy, right, our common ion, and these are going to be our x values, again dividing by our total liters to find our new molarity, and we just plug and chug into our K, just like our opposite K that we just did. So what does this graph look like? Just the opposite, right? So we started out with a weak base. We're titrating it. This is our buffer area, all right? And now we have our equivalence point down here. It is going to be less than 7 because when the base is neutralized, now we're making that weak acid. So to recap, compare moles of both strong and weak acid base. If you have strong and strong, which one do you have more of? If you have weak strong, what do you have more of? And now we got to figure out where are we in the titration curve. If we got more weak stuff, we're in the buffer area, we can use the HH equation. If we have equal amounts, that means we're at the equivalence point and we have to use the opposite K. If you have more of the strong stuff, then you're going to deal with it like a strong problem. Next, remember, moles stay the same, but molarity changes. So find the new molarity using the total volume. So hopefully that all makes sense. I think we're done with all of the titration information, all the titration curves. So hopefully you can do all of those types of problems between your titrations packet and the titration notes. See you in class.